There. Okay, so today we're going to move on to section 1.6 over nested quantifiers, and I'll explain what this word nested means in a few minutes. So this example, this first sentence, is the kind of thing that we're going to be looking at today. Let's just read it through. It says the sum of any two positive real numbers is positive. So what I want to do before we get to, the definitions and the stuff like that is just try to break down this statement and see what it actually is saying. And to get us started, I wrote down a question. How many variables are there in this statement? So you might remember from the last section, 1.5, where we were talking about quantifiers to begin with, there was this idea of the propositional function. So we're thinking of plugging variables into some function that gives us our proposition, our statements. So how many variables are there here? Well, the key word is this one, the sum of any two positive real numbers. Maybe we can just box that. So we're going to be adding two things. That means there's actually going to be two variables this time instead of one variable like we had in all of our propositional functions last time. So there's two. Let's see, and it sounds like someone's microphone is open. Is there a question or is that just accidental? Okay, I guess it was just accidental, or maybe someone was just logging in. Okay, so there are two variables, and whenever we're looking at, well, a word problem in math, it's a good idea to name your variables before going any further. So we have two variables, let's call them x and y. And we know a little bit more about these variables. So let's go ahead and work that through. We know that there are two of them, and they're going to be positive real numbers. So let's write that out. X and y are real numbers. And this sentence here tells us the domain of discourse. So that's the set where our variables are coming from. Okay, so continuing to break it down, let's see if we can rewrite this using symbols and our variables instead of words. So two positive real numbers. Positive means that they're going to be greater than 0. So we know that x is greater than 0 and y is greater than 0. Let's just write that down. If x is greater than 0 and y is greater than 0, then there's another part of it. The sum of them needs to be positive. So x plus y is also greater than 0. And this conditional statement is going to be my functional, or excuse me, my propositional function. So I have a function which I'm calling p, and I'm plugging in my two variables. X and Y to get this statement or sentence. And we can go a little bit further with our symbols because we have symbols for if then propositions, and we also have a symbol for and. So let's use those. So X is greater than 0 and Y is greater than 0. That's going to be our hypothesis for the if-then statement. So I'll draw an arrow pointing to the right to the conclusion. X plus Y is greater than 0. Okay, so I have the names of my variables. I've worked out what my propositional function is going to be with two variables. I know the domain of discourse. The only thing left now is to deal with this word, any. So this is going to be our keyword for the quantifiers. So which quantifier does this word correspond to? The there exists quantifier, the backwards E, or the for every quantifier, the upside down A? What do you think?
There exists.
Okay, so there's a little bit of disagreement. Any it's a plural word. It means for any possibility of real numbers, of two positive real numbers. And that corresponds to the word every, the for everyone. So that's the upside down A. Remember, this symbol means for every, for all, and it also means for any. So there's lots of ways to translate this into English that you need to be able to recognize. So this quantifier is going to correspond to both of our two variables. So when I'm rewriting it, the whole sentence in symbols, I'm going to need two of the universal quantifiers, the for every quantifiers. One for x, the first variable, and another one for y, the second variable. And then I can write my propositional function since we have shorthand for that. I can just write p of x comma y. Or you can write it out the long way. You can write out all of the symbols. Your two quantifiers for all x and for all y. If x is greater than 0 and y is greater than 0, then x plus y is greater than 0. So this sentence the first example here gets translated symbolically into a proposition that has two quantifiers. Are there any questions before we give that definition? Okay, so since there aren't any questions, let's go ahead. Mind-blowing. Well, if there's something that's kind of mind-blowing, I guess, if you want to use that word, it's how such a simple sentence to say in English means something pretty complex when it comes to logic. Okay, so now let's just give this idea its name. Expressions with multiple quantifiers, like this one. So we have two for alls, upside down a's. These are called nested quantifiers. And it sounds like someone's microphone is maybe open. Okay, you fixed it. A bit confusing knowing the variables and how the setup works. Yeah, so that's why we're going to practice a bit more. Because there's different combinations of quantifiers that we need to be able to deal with. And of course, there's different ways of saying them in English that you need to be able to recognize. So that brings us to this little table that we're going to fill out. Since we have two quantifiers, the universal one and the existential one, there's going to be four possible ways to combine them. And let's just work through all four of those. The first one is the one that we already did, two universal quantifiers. And I'm also going to fill in a way to, oops, I need two different variables here. An x and a y. So we're going to also write a way to express the two quantifiers together in English when they're nested. And this one is one that we've already seen, but there's maybe a more common way of writing this in English, and that would be maybe something like this. For all x and for all y. And then your statement would continue. And something to remember is that this word all can be changed around to other options. It could be every, you could see the word every here. Or like in the example up above, you could see the word any. So for every x and for every y, or possibly for any x and for any y. And now instead of the two universals, we could have one universal quantifier and then one existential quantifier. So here we have for all x, and this one says there exists a y. And we can just say that in words, for all x, there exists a y, and that would be how you translate it. And then your statement would finish with something after that. And you can reverse the order of the universal and the existential quantifiers. So we could start with the backwards e, the existential, and then have the universal second. And this says there exists an x to begin with. And then this says for every y, or for all y. So in English, you might say such that for all y. And then you could finish it off with whatever you needed. And then the last possible ordering is to have two existential quantifiers. So two backwards e's. And this one, a common way to say it in English would be there exists an x and a y. And then you would finish off your sentence. Okay, so these are all of the possible combinations for two quantifiers that you're going to see. It's possible to have three quantifiers or even more, though you won't see those nearly as often as one or two. Are there any questions over this little table? Okay, so we've already seen one example. We've seen an example for this first possibility. We need to look at examples for the other three next. Oh, and I guess before we move on, let's look back at that first example and let's see if we can determine its truth value. What do you think? The sum of any two positive real numbers is positive. Is that true or false? True, right. If you add two positive numbers, then you're going to get back another positive number. Yeah, this isn't anything that you don't already know. Good. So let's look at this example. For all integers x, there is an integer y such that x plus y equals 0. So which kind of nested quantifier are we looking at from the table? Which of the four? That's the first question, or one of several questions we need to answer.
It's for all x, there exists a y.
Right, so what symbol would I use for this?
The upside down a,
The A, and for this one,
the backwards e.
the backwards E. So we are looking at this kind of nested quantifier. Good. And the next question I might want to think about is, well, what's the domain of discourse? What kinds of things am I even talking about? Any ideas? Integers, good. So x should be an integer and also y should be an integer. And when we're talking about nested quantifiers, we're actually going to end up talking about these guys. So you might remember this is the Cartesian product from the first section. Which is kind of just a fancy way of saying ordered pairs of integers in this case. Because we're plugging in two things. And this idea of using ordered pairs comes from the functional notation that we're using. Because we're plugging in two numbers into our function, we're plugging in, well, actually an ordered pair, x and y. Okay, so I know the kind of nested quantifier I'm using. I know my domain of discourse. Now let's think about what our propositional function is. What are we actually plugging x and y into? Well, it's this here. This equation is the proposition. So a way to write this, go ahead. Was there a question? Okay, I guess that was just someone's microphone turning on. So when I plug in my two integers, what I get is an equation, x plus y equals 0. So using all of this information, we can now rewrite the sentence using symbols. We start with our nested quantifiers. For all x, there exists a y. And then you can either just write the propositional function p of xy, or you can write out the equation. That would look like this. For all x, there exists a y such that x plus y equals 0. So either of these two ways work to express the sentence symbolically. Are there any questions over how that worked out before we think about the truth value? The propositional function. So in order to get that part, I just had to look at what the sentence was actually telling me about the variables x and y. So this first part of the sentence, for all integers x, there exists an integer y. This has to do with quantifiers. The next part of the sentence, the part after such that, is what it's actually telling me about the two variables. So this is where we can find in the sentence the propositional function. Good question. Okay, so let's think about the truth value. Is this sentence true or is it false? So if you give me an integer x, can you find an integer y so that when you add it to x, you get 0? Maybe I'll write out that question. Right, it is true. So here's the question that I was asking. If I give you an integer x, can you find y? So that x plus y equals 0. And you can even make this question a little bit more concrete. So let's say I gave you the number 5. What would your answer be? What's the integer y? Minus 5. What if I gave you the integer minus 103? Minus 103. What would your answer be for y? Positive 103. Yeah. And I think someone was about to say that on the microphone. So if I give you x, you're going to give me back negative x. And we can write that out. If y equals minus x, then x plus y, I can plug in my minus x. To get 0. X plus minus x is 0. Good. Any questions? Okay, so then let's think about this next example. This one I'm giving you in symbols. And our first step is going to be probably to translate this into English so that we can understand it a little bit better. So how does this one compare to the previous example, the one that I've boxed up here?
The for all and for there it exists are switched.
Right. So here we have the for all and there exists. And in this next example, we're starting with there exists, and then we have for all. And so what we're going to be looking at this in this example is what happens when we switch the order. And also this is the, going back to the table on the last page, this is the bottom left one. So just reading through it, we have the symbolic expression, and we know that the domain of discourse is z cross z, so ordered pairs of integers again. So when I'm talking about x, I'm going to be talking about an integer, and the same thing for y. So the first one is the existential, there exists an integer x. And then the next part is the universal for all. or for every. So there exists an integer x such that for every y, every integer y, x plus y is equal to 0. So that's how it works out in English. We're just swapping the order of there exists and for every. Let's think about the truth value. So we have one true, one vote for true. I guess that's 2 votes for true. So can you think of some integer x so that for every other integer y, when you add them together, you get 0? Can you think of this integer? So can you think of just some number? Oh, right. Someone's changing their answer. Right. So when we switch the order of the when we switch the order of the quantifiers, we actually change the meaning of the sentence quite a bit. So I'm saying, or if you wanted to say true, you would have to give me an example of an integer so that when you add it to every other integer, you get 0. So if you think of an integer, just pick a one, like the number 1 would work. If you add any other number to it, you're not going to get 0 unless your other number happens to be -1. And that same kind of idea works for any integer that you might pick. The only number that when you add it to the one that you start with, that you get 0 is the negative of what you started with. So this is false. And well, you can solve this equation to help you see that. Move the y to the other side. Or actually, it doesn't really matter which one you move. X equals minus y or y equals minus x. There's only one choice. So our conclusion here from this example is that that order of the quantifiers matters. If you switch them, you're probably going to switch or change the meaning of what you're saying. Any questions over that? Okay, so the next possibility for our nested quantifiers is this one. So 2 existential quantifiers. So just take a look at this symbolic statement, we're getting a little bit more complicated. And then keep in mind the domain of discourse. This is Z plus cross Z plus. And those are ordered pairs of positive integers. So keeping in mind that our variables x and y are going to stand for positive integers, we can start translating this into English. So we have two existentials. There exist positive integers, x and y, such that, and now we have to write down the rest. Is that where you get p of x comma y from? The ordered pairs, yes. Well, here the x and the y tell you that you're plugging x and y into this statement. So this here, if we need to think about the propositional function, this is going to be p of x comma y. So we're trying to translate this one into English, so we're not worried about the symbols just right now. That's more for when you're trying to translate it the other direction, from English to symbols. So now we need to look at this stuff, and you can see that there are two and symbols, and then there are three parts to it that are being connected by the ands. So we just need to write them down. X is greater than 1. Y is also greater than 1. And the last equation, x times y is equal to 10. Okay, so now that we have it in words, let's think about the truth value. Is that a true or a false statement? It's true. Can you think of two numbers that'll work?
6 and 4.
6 and 4. Oh, so when you add those together, you get 10.
Oh.
This is multiplication.
Oh, yeah. 2 and 5.
2 and 5. Yeah, good. And let me tell you what the conclusion of this, since it might not be totally obvious what I'm getting at. So you have to think back to what prime numbers are. And what we're saying here is that the number 10 is not prime. Remember, a prime number is a number that can't be divided, essentially. So the only positive integers that you multiply to get the number have to be 1 and the number itself in order to have a prime. And this one is not prime, since 2 times 5 is equal to 10. And let's go ahead and compare that to this next proposition. If you compare the two, this one and the next one, the only thing I've changed is this last bit, this last part of the and statement, x times y equals 10 up here, and x times y equals 5 in this other. So when we're translating this into words, there's only one change we have to make. There exist positive integers x and y such that x is greater than 1 y is greater than 1, and x times y equals 5. So is this one true or false? It's false, because 5 actually is a prime number. Good. Okay, so any questions over this last combination, this last type of nested quantifier? Okay, so to move on to the next, or the last topic that we need to talk about, is how De Morgan's laws relate to nested quantifiers. And so you might remember from last section, De Morgan's laws are what happens if you add negations. They tell us what happens if you add negations to quantifiers, or ands and or statements. So what I want to do is just think through what would happen if I put a negation symbol on this nested quantifier. So I want to use the laws that we learned at the end of section 1.5, what your textbook calls the generalized De Morgan's laws. Okay, so I'm putting a negation symbol and then copying down the nested quantifier. And then we'll just work through what the De Morgan's laws told us to do. And in summary, what they said is that you should distribute the negation inside of your quantifier, and you have to switch the quantifier in order to do that. So an existential becomes a universal, and a universal would become an existential. And you have to work with nested quantifiers from left to right, the same way that we would read it. So I would distribute this one inside of the existential and switch the existential to a universal. Something like this. You wouldn't switch the universal. So that's what I'm going to do next. So we distributed the negation inside of the existential, and now we have to distribute it inside of the universal. So in order to do that, well, I'll leave this first one alone, and then this one will switch to an existential quantifier, and then I'll move the negation further inside. So we'll get a not p of xy. Good. So that's how that works. So the conclusion is that you would swap all of the quantifiers. Here we have E and then A, and now we have A and then E. So they both get switched, and the negation moves all the way to the inside. And I think we have just enough time to maybe talk about the last example here. I want to find the negation of this nested quantifier that says for all real numbers x and y, oh, excuse me, for all real number x, there exists a real number y, keeping in mind the domain of discourse, such that x times y is less than 1. So what I want to think through on this example is the negation of this. So put a negation symbol on the outside, and then copy down the proposition. And then you can work step by step, or you can do it all at once. I can go write it out step by step, and then we'll finish up. So distribute this inside of the universal to get an existential. And then do that again so that the existential becomes universal. And then you can add the negation just on the outside of this inequality, x times y is less than 1. Or we can go ahead and just switch it around and say x times y is greater than or equal to 1. So it looks like I'm out of time, so I need to stop there. And I'm going to leave you maybe a little exercise to think about. Just on your own. Oh, this question isn't homework. I will be adding a homework to Blackboard. This is just something for you to think about. Think about what the truth values are for the original statement and the negation. Just figure out which one is true and which one is false.